Hello, Mr. Collier here. Today we're going to give some notes about Chapter 4, Atoms and Moles. The focus of this first discussion is going to be about some of the history of atomic philosophers. So the very first people to think about atoms and molecules were the Greeks about 400 years BC. And one that kind of gets the most credit was someone named Democritus. And he presented this idea of atoms, the idea that matter at some level was indivisible. Aristotle, who is a lot more famous in many regards, disagreed. He didn't believe in atoms. He thought matter was continuous, meaning at some point it was always still divisible. Turns out he got that one wrong. So for about 2,000 years, Aristotle's ideas prevailed. But by the 18th century, we started to get some experimental evidence proving Democritus right and Aristotle wrong. By this time, most people thought that an element was something that could not be broken down into anything further and that it could combine with other things to form compounds. They weren't really sure, however, how they combined and what ratios they were. But eventually we developed better balances which allowed them to study chemical reactions and actually measure them quantitatively while they did it. So these really accurate balances allowed us to mass reactions as they were happening and figure out everything we know about atoms. This led to the law of conservation of mass, which just says that as long as nothing enters or leaves a chemical reaction, the mass remains constant. It also led to the idea of definite proportions, which says that regardless of the size or the source of the sample, the elements that make it up are always in the same proportion. So like water is always H2O. It also led to a deeper understanding that certain atoms might link up in different ratios. This is the law of multiple proportions. So any two elements might combine in a variety of different ratios. But if they do, and this is the important part, it's always a ratio of small whole numbers. So like CO is carbon monoxide and CO2 is carbon dioxide. Both are carbon and oxygen. They can link up in different ratios. Nitrogen and oxygen do this as well in lots and lots of different ways. These three laws led to a guy named John Dalton proposing his first atomic theory, and this is really where modern chemistry begins. He basically said, all matter is made up of indivisible, indestructible particles called atoms. He noted that atoms of the same element are chemically and physically the same. He also noted that atoms of different elements are chemically and physically different, and that when atoms combine in a chemical reaction, they do so in small whole number ratios. He also noted that in a chemical reaction, atoms aren't created or destroyed, they're simply rearranged. After John Dalton, the modern atomic understanding that we have started to come into focus, and I'm going to go over some of the structure of what atoms are made of and how we came to understand that now. So first of all, atoms consist of two regions. One of them is called the nucleus, and that contains protons and neutrons, which are these smaller than atoms things we call subatomic particles. Subatomic particles make up atoms, but they themselves are not atoms. You need combinations of them to have the different atoms. The other area is the area around the nucleus. This contains the negative particles called electrons, and all of them together are known as the subatomic particles. Now I'm going to talk about each of the subatomic particles and when and how they were discovered. So the first one we figured out was the electron. This was discovered by working with a tube that contained a gas at very low pressure. When you put electricity through that, it would light up. This technology is called a cathode ray tube, or CRT, and this was what was used in televisions for years. What they found was that by making this ray of beams, it would be deflected by a negatively charged magnet or something that you brought near it. And that showed that the ray itself had a negative charge. And the fact that that little ray that was produced would move a paddle wheel showed that it was a particle. So we figured out that it was negative and that it was a little particle, and along came our understanding of the electron. It turns out that the ray itself was made of electrons, and the scientist credited with naming it is J.J. Thomson. He called this model the plum pudding model. He thought that atoms were these little squishy spheres that had negative electrons stuck in them like raisins in a cookie. So it made sense that if there was a negative charge, there must also be a positive charge to balance it, because atoms on whole were found to be neutral. And it was Ernest Rutherford and a few associates that figured this out. They did an experiment where they bombarded gold foil with these things called alpha particles, which are tiny positively charged particles. They expected that most of the alpha particles would go straight through, and for the most part this was true, but some were deflected and some shot straight back. Below is an illustration of that gold foil experiment. You've got your alpha particle creator, then your beam of alpha particles, and it hits the gold foil. This screen detects anything that hits it, and it found that many of the particles went straight through, but some were deflected, some bounced almost straight back. What this showed was that while the atom was mostly empty space, there was a dense portion called the nucleus now, and that dense portion was able to deflect these positive particles, which meant that the nucleus was also positive. So again, Rutherford's gold foil experiment developed this idea that atoms are mostly empty space, that's why most of the alpha particles went straight through the thin gold foil, but that there's a densely packed positive nucleus, and that's why some of the alpha particles, which were also positive, got deflected. Also through this experiment, Rutherford discovered that there are actually three types of radiation or radioactive decay. Alpha particles was the main thing he was using in this experiment. They are positively charged. Beta particles, which are negatively charged, and gamma rays, which are high energy X-rays. What he concluded from his experiments with radiation was that the alpha particles were drawn just slightly toward the negative plate. Since they were drawn toward the negative plate, that meant they were positive, and since the attraction was slight, it must mean that they were relatively large. Beta particles were drawn greatly toward the positive plate, which meant that they were negatively charged, the opposite, and that they must be small because of how greatly they were drawn. And finally, gamma particles were not deflected, which meant that they were neutral and they had no mass. This little illustration kind of sums that all up. So to summarize the subatomic particles, electrons are the smallest and the lightest. They can be found outside the nucleus. They have a negative charge. Protons and neutrons are the heaviest. They're found in the nucleus. Protons are positive and neutrons have no charge, or they're neutral. Here is a diagram of the Rutherford model of the atom. Protons and neutrons in the nucleus, electrons outside it, and the electrons are teeny tiny. We consider them to have basically no mass because you would need almost 2,000 of them to have the mass of a single proton. Protons and neutrons have about equal mass. There are a few more scientists to know. You might have noticed that we haven't really talked about the neutron. Irene Curie made a beam of particles by bombarding beryllium with alpha particles. James Chadwick then took that beam, that science that she had done, and tried to bend it with magnets. It wouldn't bend though. This meant that the beam that was created was neutral, and he discovered the neutron. Niels Bohr was someone who worked with electrons and their energy levels. So far I've just said that electrons exist outside the nucleus. We'll go into great detail in this in a future chapter, but Niels Bohr was the first to present the idea that electrons were in different energy levels, some closer to the nucleus and some further, kind of like the planets around the sun. Some are closer and some are further in different orbits. So just to quickly summarize, Dalton thought that the atom was indivisible. Thomson experimented with cathode ray tubes, discovering that electrons were negatively charged particles. He thought the atom looked like plum pudding, which meant that he thought the negatively charged electrons were stuck into a lump of positive stuff. Well, it turns out that wasn't the case. In actuality, Rutherford discovered that it wasn't positive goop. It was a gold foil experiment, which discovered that it was mostly empty space. The gold foil experiment shot alpha particles at gold foil and discovered that protons are found in a dense nucleus and the atom was mostly empty space. Then Chadwick and Curie discovered the neutron by bombarding beryllium with alpha particles, creating a new beam of particles that had no or neutral charge. Then Bohr described the atom as having electrons in different energy levels, further or closer from the nucleus. Now, one last new thing. Electrons can actually change which energy level they're in, the ones closer and further from the nucleus. The ones that they're normally found in are called the ground state, and when they go to a higher energy level, we call this the excited state. That happens when energy is added to an atom. The amount of energy that is added will cause the electron to move from a certain energy level to another. This is called the absorption energy. However, in this excited state, they are unstable, and when they fall back down, they'll give off electromagnetic radiation in the form of light. This is how you make glow-in-the-dark stars. This is why fireworks give off the colors they do, and we'll study it in more detail in this chapter. The light that is given off is called an atomic emission line spectra, and each element has its own line spectra that we can use as a fingerprint to figure out which element is giving off that color. We'll be doing a lab with this in class.